It is new unit day, unit 4. So we have one more unit after this, modern physics, um, special relativity, things like that, you'll see. But this one, unit 4, we're talking about light, the nature of light, and it's about about basically wave properties or particle properties of light. So we're going to look at rectilinear propagation, which is a really fancy way of saying it travels in straight lines, reflection, the universal wave equation from grade 11, connection between wavelength, frequency, and color, and so on. So those would be wave properties of light, obviously. Um, so there was a good period of time where there was a pretty big debate in physics about whether or not light is made up of particles or if it's a wave, right? So you got particles, you think of it as photons. And we saw previously those are the exchange particles for the electromagnetic field. And then, the idea of it traveling as an electromagnetic wave, we've talked about as well. So you've actually kind of already heard about both of these ideas, right? And they're both scientific models. The purpose of scientific models is often, in a way, to help us feel like we understand things, help us explain observations. And the quotes are because sometimes it's not really an explanation. Sometimes it's just, feels good, if you will. And certainly this is the major benefit that we help predict. It helps us predict new observations. So some examples, right? The planetary model, the atom is a good example. We teach it in grade 9 and 10 as if the electrons are orbiting around a positive nucleus, attracting to the nucleus because of opposites attract and so on. And certainly helps us feel like we understand what atoms are. It explains, in quotes, chemistry. We talk about how unstable atoms are ones with a few electrons in the outer shell, or missing a few, or have a few, right? And that they're stable if it's a full shell. But explain being in quotes, if you think about it, no one really says why. Like in grade 9 and 10, at least, anyways, no one talks about why they're stable if it's full. It's just an observation of the world around us, right? And so, if we look at this model along with quantum later on in reality, but we can predict and explain the absorption and emission spectrum. So atoms absorb certain colors of light and emit certain colors of light. And of course, the idea is that the electrons absorb energy. So if electron absorbs this amount of energy here, this corresponding to that particular color, then it jumps up a certain amount. And then when it drops back down to its normal energy level, then it gives back that same color, right? So absorbing energy or giving it back, right? So it turns out later on you'll see that mechanics, in other words, treating light as particles, is needed to explain this thoroughly. Again, why particle nature of light is needed is subtle and not an obvious thing, but we'll get there. It's not yet. So some historical information going back here. The Pythagoreans, way back, light travels as a stream of fast-moving particles was their thought. Empedocles, I believe that's how you pronounce that name. Empedocles, I think I used to say, but I think it's Empedocles. Was a basically an opponent, or basically thought differently, right? That light travels as a wave-like disturbance. So even way back then, right, the particle or wave debate began. The Greeks, Plato, thought light consisted of streamers or filaments, right? So like photons, like little particles, right? That were emitted by the eye, though. Kind of took a step back in logic here, right? Kind of like echolocation, though. You bounce things off and see when they come back and figure out the world around you based on that, right? So they'd bounce off things, allowing you to see and so on. And then, of course, evidence against this, someone realized, like, well, why can't we see in the dark then? But yeah, so particle versus wave, the big debate, and in more modern times, was Newton versus a person named, which everybody's heard of, Isaac Newton, from Newton's laws and so on. The wave camp was led by Christian Huygens. And yeah, so of course Newton wanted his laws of motion to apply to light. So he kind of was a little bit biased, if you will, because he was really hoping his ideas to do with motion of particles would just, extend the light and make him even more accomplished than he was. And he had people on his side. Laplace, if you look up information about that mathematician, scientist, physicist, Laplace, you know, he was on Newton's camp, agreeing with Newton. Robert Hooke was supportive of the wave property, and you might notice that name two ways. You might have heard of him in grade 9 or 10 as the person who invented the microscope, and also, of course, Hooke's law to do with springs, right? So, I included the old Wikipedia bio of these people as a start, anyways. At least if you want some more background information about, you know, things to do with them. But certainly, as each of these says, you're not memorizing this stuff. I'm not going to quiz you on it or test you on it by any means. It's just kind of knowing some history about the world around you. So evidence of things, right? So the debate, and look, we're going to be looking at the evidence of particle nature versus wave nature, and it's going to be an ongoing theme for a while. So whenever you see the evidence continued, talking about, you know, what we have discovered around us and what that says about the nature of light, right? So light travels in straight lines. That's the rectilinear propagation thing. Sharp edges on shadows, rays of sunshine. You see it all around you, right? So particles, particles travel through the air in parabolic paths. If you look at a basketball shot or a baseball hit or something, but the faster a particle travels, then the straighter the path it goes. So Newton looked at that and said, okay, well, light must be a really fast moving particle. So even if light's not particles, right? You can see this model kind of led to something that makes sense. Light really is fast, right? So yeah, that's the power of a model, right? So they must have a really small mass, if any, since you can't feel light hitting you, and that's true as well. So there's the sort of logical conclusions that come from thinking about things, even if light's not a particle, or even if light's not a wave, or whatever the result ends up being, right? Newton said that light can't be waves, since waves have curved edges, right? Picture a circular wave in a pond radiating out and so on, right? But Christian Huygens, I want to say actually right away too, to me, it's a pretty weak argument from Newton. If you look at a light bulb, light radiates out much like that, right? So anyways, Huygens though, came back with this idea of these wavelets that we think of as ripples in a pond. If a whole bunch of them all line up in a row, you get this like straight wave front, and that could be like a pulse or that's the traveling in a straight line idea. So, which from the grade 11 course, this would be constructive interference along the front. I'm going to be mentioning a lot of things from the grade 11 course. I understand some of you may not have seen the waves and light unit, unfortunately, from grade 11, but I'm going to be reviewing over, and so you're going to see it for the first time, and grade 11 students are, just reviewing over it. So obviously a little more familiar if you've seen it before, but I'll make sure to show everything that we need here, at least in an introductory way. Anyway, so yeah, at this point, there's not really a conclusion from this, but these are just ways you can, the two different theories can kind of justify that light travels in straight lines. There are going to be times where we're going to be saying that the particle theory or the wave theory can't justify an observation, and then that gives you evidence that for one wave or versus another. Okay. So let's look at reflections. So to satisfy the law of reflection, angle of incidence equals angle of reflection. Newton did this with collisions, and so basically he said, corpuscles was his name for particles of light for some reason. It was a different time, but yeah. So he's saying, okay, well, they must be perfectly elastic collisions. Then this matches my ideas to do with particle collisions perfectly. Yay me, right? So yeah, nice application of Newtonian physics to light, really. Huygens, though, said, well, waves reflect too, so there's nothing, there's no problem here, right? If you look at this little applet here, the result shows, waves coming in, waves going out, reflecting, and so on, right? So as you've either seen in grade 11 or seeing for the first time ever, but you've seen waves reflect off of docks and go out other ways and stuff like that, I'm sure. Life. See why this isn't clicking here. All right, so here's the applet. And so I don't know why it's so slow right now, but wavefront coming in, and then it's not doing what I want it to do right now. It's not showing the reflection. I guess next step. I don't know. Not showing the reflection. I don't think it's working properly anymore. This is the wavelets though, little ripples from each of these things. Oh, there we go. We have to have the ripples to show the reflection. So the direction it's coming in at is like this, and then the direction it's going out at is like that. So if you think about it, you're going in and out on those angles, and you could think of this as a laser beam going in and out as well, that wave front. So either way, you got going in at 45 and out at 45, right? And you can, I don't know if you can change the angles and stuff like that too. If you go in at 60 degrees, and so on, and it'll go out. So basically showing, wave properties have no problem explaining or showing that waves reflect, right? Other characteristics of waves review in connection to light. So waves from grade 11, they're a transfer of energy, right? They can be longitudinal or transverse. So that means that longitudinal would mean if the wave is traveling, let's say left to right, then the vibration of the particles are left-right as well. So that's a compression wave, like a sound wave. And transverse would be if the wave's going to the right, the particles would be going up and down. That's like a water wave. So this link here gives you a kind of review of those properties of waves. So if you need it, it's there for you, okay? So I recommend, if you haven't seen that stuff in grade 11, you definitely want to watch through that. But yeah, so there's the diagram to transverse I was talking about. We talk about the speed of a wave is, a quantity that can be measured, of course, and so on. This listed here, the light in a vacuum has the fastest known speed of 3.0 times 10 to the 8 meters per second. Travels slower in other materials, basically because it interacts with the material, slows it down. The frequency, I mentioned frequency in an earlier lab, right? That's number per time, right? Cycles per second, you see here. And wavelength. Wavelength is the length of the wave, so the complete pattern that repeats, right? So, this top, back to top, and then it goes top, back to top again. Or you could start here. It goes from the middle, up to the top, down to the bottom, back up to the middle. And then it goes up to the top, down to the bottom, and so on. So however you think of a complete cycle of the vibration, so the pattern, it can be like that, right? That repeats over and over again. I can show here where it would be there, and then there it is again, and there it is again. Apparently the picture's not perfectly uniform here. Or we could start here and go up and down and back up, in which case that's going to happen over and over again as well. Either way, that length from the start to the finish is your wavelength, literally the length of the wave, right? And in grade 11, we justified or developed or whatever, but the idea of this, where we have speed equals distance over time, while the distance a wave travels is wavelength, and the period of it, the period is just how long it takes the vibration. Say this, picture this being a vibration that goes up and back down and up, right? And then that sends that wave out in that material. And so, someone jumps in the water's pushed down and up and down and so on, and then that wave goes out. So the amount of time it takes the vibration to go all the way up and all the way down and back is the period. That's the big capital T down here, right? And so that solves eventually here, if you look at it, it becomes V equals F lambda, which is called the universal wave equation, okay? So that's going to be something you got to just become familiar with if you haven't ever used that, but it's basically just velocity equals distance over time, but it looks different because it's in terms of wave properties, right? Frequency and wavelength. With light, the wavelength and the frequency correspond to different colors. That's important to know. So that's kind of new for everybody. But I think it's kind of already obvious or known or whatever, but the speed of light's always this 300 million meters per second. And then you're going to have frequencies and wavelength combinations that match that speed, and we see them as different colors. All right, so there's all your different values. So you see the higher frequency end of the spectrum corresponds to lower frequency or lower wavelength, of course, right? Because if the vibration is going up and down quicker, the wave doesn't have as much time to travel, so it makes a smaller wavelength. So it all makes sense. This higher frequency end corresponds to higher energy. Think about like the vibrations going more, more cycles per second. That's more energy. So that should be obvious and kind of easy to sort of commit to knowledge as well. Down in the red end of the spectrum is your lower energy, right? So the vibration is going like not up and down very quickly, which makes the wavelength longer, the wave has longer to travel sideways or through. So we're visualizing these as transverse waves. Now, again, scientific model wise, there's no actual physical vibration. When you look at ripples in a pond, the water is physically moving up and down, and the wave physically travels sideways, and it's a transverse wave. We're thinking of this as ripples or vibrations in the electromagnetic field, and we visualize them as transverse waves. Okay. Soon, oh yeah, here this was frequencies in terahertz, the big capital T. So it's, you're going to over time become more and more familiar with all these metric prefixes. So terahertz, and the wavelength actually as well was in nanometers. And so nanometers is 10 to the negative 9, tera is 10 to the 12, but you're already familiar with like centimeters and kilometers, kilo meaning 1,000. So these are just a bunch that you'll gradually get more and more familiar with as you see them more and more. Notice that the visible spectrum of electromagnetic waves is, of course, visible light, but there is all these other, versions of electromagnetic waves. And so microwaves and radio waves and infrared and ultraviolet that you get sunburns from, and X-rays and gamma rays, these are all different manifestations of the same thing. So these gamma rays and X-rays would be the electromagnetic kind of radiation, whereas in grade 11, you probably hopefully also saw the idea of particle radiation, right? Like where helium nucleuses, alpha particles, things like that. But so it'd be dangerous to say that radiation's always the same as light, because it's not quite, right? There's the particle version as well, but high energy stuff that ionizes, damages things. And the end here, worth repeating, of course, the fastest known speed, right? The fastest possible speed. We're going to see later on in the course that it's actually the ultimate speed limit for anything. That's when we get to the modern physics stuff in the final unit, unit 5. And so this is basically a chance to see the universal wave equation working to do with light. So in grade 11, in the waves and sound unit, you use this equation to describe water waves and sound waves and so on. Now we're using it to describe light. So, I view that as pretty strong, evidence of the wave nature of light. It would make sense since these numbers all work, right? So there's your speed, there's your frequency, and the question is, what's its wavelength? And we could even ask like what the color is later too, stuff like that, right? Now, mind you, you get the color based on the frequency itself. Go back to the 560, right? So 560 would be in this green range. So anyways, yeah, so this would be 560 terahertz means 560 times 10 to the 12, or if you're writing it in proper scientific notation, 5.60 times 10 to the 14. Numbers just go in, right? Just plug them into V equals F lambda and rearrange if necessary, or plug them in. Yeah, plug them in and then rearrange, or rearrange, then plug them in. Either way is fine. My preference is kind of always to put the numbers in and then just do the algebra afterwards, but it doesn't really matter. Yeah, so we get that number, and of course, if you picture the decimal being there, that would have to be a 1, 2, 3, 4, 5, 6, 7 steps, right? So 5.35 times 10 to the negative 7. I'm noticing I didn't put a negative in here. Wrong spot here. Negative 7. And or in other words, 5.39 times 10 to the, I missed all my negatives. Negative 9, right, meters, or in other words, 535 nanometers. So yeah, the wavelength is 535 nanometers, and you look and see in the spectrum, and you see that it's green. Okay, so yeah, so when you're using V equals F lambda, with light, have appreciation for the fact that we're looking at wave properties of light. And that's a good little review of some grade 11 stuff there. It's not hard, even if you haven't seen it before. And yeah, so this is, grade 11 stuff where you're doing V equals F lambda for water waves. And then, yeah, with light. So again, the main focus overall is this wave particle kind of property analysis of light. So, alrighty, that is it for now. Thanks for watching.